let's now derive our formulas for geometric series and see if we can come up with one for that. So sum to n, if we were to add all the terms up, we've got a plus ar and so on and so on and so on, and the last one would be ar to the n minus 1. This time I'm going to rewrite it, but multiply every term by r. And I've just sort of shifted the terms along a little bit to make it a little bit obvious why I've done that. Because if you look in the columns with our simultaneous equation, you'll see we've got AR over AR, AR squared and so on. So I can do a subtraction here. And where this dot dot dot, where I don't know how many terms are because it's a general formula, it doesn't matter because all the way along they would be cancelling. The only ones that aren't going to cancel is the A in the first line and the AR to the end in the second line. So if I subtract, and I've done the bottom one minus the top one, I get r minus 1 sum to n is AR to the power of n minus A. Divide by r minus 1 and we get the formula that you may be used to seeing. Now we tend to use that formula if the ratio's bigger than 1. Or it doesn't matter about the plus or minus, I'm just talking about the actual magnitude of the number. So we tend to use that one. The only reason why I can think of is so that the bottom, because again we're thinking about positive ratios, so that the bottom ends up being a positive number. Because you've got a number bigger than 1, subtract 1, it's still going to stay positive. Because we then say, well hang on, if the ratio is smaller than 1, then we'll make it 1 minus r. And again, if I sub it into that one, well 1 minus a number smaller than 1 ends up being a positive number. That's the only reason I can see that we do it. They are exactly the same formula. All we've done, if you look at it, is multiply the top and bottom by -1. So it actually doesn't matter. I mean, if you wanted to use the first one and the ratio is smaller than 1, it's going to work. And if you wanted to use the bottom one and the ratio is bigger than 1, it's going to work. Okay. So it's more for convenience that we have these two. They are in fact the exact same formula. Now, with the geometric, we have this limiting sum, or sum to infinity. But it only works if the magnitude of the ratio is smaller than 1. Because that way, each of the terms, if it's smaller than 1, and we're multiplying by that number, is getting smaller and smaller and smaller. So in that case, if the ratio is smaller than 1, think of your graph, so maybe it's a half. If you were to draw half to the power of n, you'd have your exponential graph, but the backwards one. And as you're going to infinity, that curve would be getting closer and closer to the x-axis. So we know the limit as n approaches infinity of r to the power of n would be 0. So you've got your exponential curve, but the one that's being flipped, so it'd be going asymptotic to the x-axis. So in that case, as n approaches infinity, we can now get a value for the sum to n formula. Because the only thing that's going to change there is the r to the power of n. But we've just said, as n approaches infinity, r to the power of n would be 0. So we just end up with a on 1 minus r. And so that's where that formula comes from. It's using limits. So alright, there's another formula that we sometimes use. The sum to infinity for a geometric series, a over 1 minus r, but it only works if the magnitude of the ratio is smaller than 1. So let's have a look at some examples. So 2, 6, 18, etc., etc. Let's just do an example of using our formula. A is 2 in this one. The ratio we can see is 3. They want sum to 10 terms. So we'll use the r minus 1 formula. Substitute in. Now, I suppose it depends on your calculator how you do it. The more modern ones now can handle this sort of stuff and still spit out a fraction if it ends up being a fraction, I think. Mind you, this one won't if you look at it closely, because the denominator is 3 minus 1. So 2 obviously cancels with the 2, and we'll end up with 3 to the power of 10 minus 1, 59,048. Sigma notation, but you'll notice we're not starting at n equals 1 for this one. But it is geometric because I notice I've got something to the power of n, or in this case n minus 1 So it's in that form of a general term for a geometric series, a constant times something to the power of n or n minus 1. So alright, first term, let's sub in 3, not 1. In this case, sub in 3. So we get 6 times a half squared, which is 3 on 2. We know the ratio is a half, because it would be r to the power of. And if you were unsure what the ratio is, I suppose you could substitute in n equals 4 and just work out from that. Oh, well, the ratio is a half. And 6 terms. 8 minus 3 is 5, but it's inclusive, so we add 1, 6 terms. This time I'll use the 1 minus r formula because the ratio is smaller than 1. Alrighty. Oh, again, this one depends on how good your calculator is. Now, I'm so used to the older calculators that I tend to do it bit by bit. So I'd probably work out the half to the power of 6 first, subtract from 1 and do it that way. But as I say, some of these newer calculators can handle that whole thing and still come up with a nice, neat answer. My old-fashioned way of doing it, I would have gone, well, 3 on 2, half to the power of 6 I know is 1 on 64, so 1 minus that is 63 on 64. Bottom of the fraction is 1 minus half, but invert and multiply, so I get 2 over 1, and then I can work that out, 189 on 64. That's me being old-fashioned, so possibly your calculators will. Did anyone try it on their calculator? It came up okay? Yes, I say, they're getting better and better, the calculators at that. Question, they love this sort of question. You see it pop in every now and then, and they simply ask, does it have a limiting sum? And they want to know whether you understand that the limiting sum only works if the magnitude of the ratio is less than 1. So we simply got to look at what the ratio is. So our ratio for this one is 4 on 56. That is less than 1. So yes, it has a limiting sum. It satisfies that condition. Didn't actually ask me to find it, so don't waste time in finding it. It was simply a question, does it have one? Ah, the old frog in the well question. You know the old fable, the frog in the well, where you got the frog in the bottom of the well, stupid frog. But he jumps up half the height of the well, and each time he jumps, he can only jump half as much again, and the question is, will he ever get out of the well? He's a stupid frog. So, first term's a half, the ratio is also a half. So if it was possible for our frog to jump an infinite number of jumps, a on 1 minus r, it equals 1. So he never actually gets out of the well. He's right on the, if he can do an infinite number of jumps, he's right on the edge of the well. Now I'll come back to this sort of question. And I hope you remember how we can just look at this and bang, we've got our answer. And of course, if they wrote the question just like this, write 0.36 repeated as a fraction, I would just write the answer down. Sometimes they might say, by expressing it as an infinite sum, which I could do like so. 0.36 repeated would be 0.36 plus 0.0036 plus 0.000036 and so on and so on. So we actually have a geometric series. It will have a sum to infinity because the ratio is, what is it, 1 on 100, isn't it? Yeah, we're multiplying by 1 on 100 each time. So we could say, oh well, the A is 0.36, the ratio is 0.01. We could use the sum to infinity formula and go 0.36 over 1 over 0.01. Well, I've written it as 36 on 99. Technically, I suppose it's 0.36 on 0.99, but we usually don't leave fractions with decimals in them. So multiply top and bottom by 100, we get our 36 on 99, which is 4 on 11. Make sure you read the question, because as I say, if they simply say, write 0.36 repeater as a fraction, don't waste time. I mean, 36 on 99, I know that's what it is. So that's the first bit of theory for today.